In this video, I will again go with what I remember after reading David Tong's lecture notes on string theory. I haven't touched them for the last 3 days. Only yesterday I picked it up and go through it. This is what I remember after reading the middle section of chapter 2, where he talks about quantum theory of string. Yeah. So basically, it starts with. Let me remember it. The idea is that we can go for covariant. Yeah, the covariant gauge got a problem. I don't remember that. But the problem is normal ordering, I guess. Yeah, normal ordering. And there are solutions of it given in Witten's book. But yeah, that's what I remember in the first section. And after it, in the section 2, where he goes for quantization using Lightcone gauge. Basically what he does is he solves the string action. He finds the phase space of string action when it is satisfying some constraint, and then once he finds the phase space, he does the quantization. So it starts with, I don't actually remember the equations. Let me at least check the equations. Yeah, Lightcone gauge, and that's how it does. It's done. So Lightcone gauge. So basically, there's the idea of gauge fixing, and then there's some issues of zero measure, as well as when you do some transformations, you get the conformal factor, and then using Weil symmetry to get rid of that conformal factor. So there are a lot of stuff I don't remember, but yeah, basically it starts with, in Lightcone gauges we do this: x plus and x minus as 0 plus minus xt 1 by root 2. We pick out two equations. Two equations. It's wrong. Two dimensions and take their linear combination, and we define these points. Then what we do is we solve the equation of motion of string. The equation of motion of string is solved in following way. What's the equation? It was initially, yep, it was this. The equation of motion, and there was one more equation, and there were two more equations which were constant, which I don't remember. There were two constants, and I think I need to remember. I really don't remember anything. But basically what happens is, that's why, yeah, we solve this equation in the classical phase, and then in classical mechanics, using classical mechanics, and we get, let's say, take this, we solved it and we got something like x, there's some factor, plus p some factor, and there were some factors, and there was summation, and yeah, that's all I remember actually. And yep, that's what I was remember. Sigma plus and sigma minus, this is traveling to left and this is traveling to right. And sigma plus minus are simply t plus minus x by 2. And this is what I remember. But what we do in here, if I gauge fix it, yeah, we do some gauge fix. We can, but it should be composed of one is, and there are coefficients here, but I can't see it. Jeez. There should be x plus when x is written in terms of left and right, we can I know we can reparameterize sigma in terms of sigma, but the idea is it has to be reparameterized in the older coordinates, so that we get only a simple scalar when as a conformal factor. I don't remember. By doing gauge fixing, somehow we are able to get it in form of this. Some coefficients. And there is an issue whether this is the right thing to say, because here we have a Lightcone coordinate and these are all constants, but tau, I think I remember it. You will be going to say L and these are going to be minus, and similarly there will be equation for XR, and then you are going to say, well, look, I'm going to now reparameterize my sigma minus in terms of Euler such that this equation becomes x plus by 2 plus p plus sigma minus something like that, I guess. And same goes for XR, if I'm not mistaken. And there's an issue, why don't we reduce these also? But the fact was that the reason he gave, which I'm not able to understand, is that sigma, because we are talking about closed strings and we have identified 0 and 2 pi, it has to be periodic in sigma. Yeah, this is wrong. This has to be tau and this has to be sigma. So you add them, sigma gets cancelled and you are left with tau, and these are the coefficients. And basically it's a time like in the space like he gives, that as long as the mass of the string is not 0. This is right, which I am not able to understand. Afterwards he does this. Once you fix these parameters, then x minus is fixed, because we have some constant equation which I'm not able to remember. I'll get back to them tomorrow. Yeah, you get some constant equations, and once you get the constant equations, what we get? Yeah, we get the for the constant, by the constant equations we get some alpha. Yeah, those coefficients are coefficient and annihilation operators, and you get those some conditions on them, but p minus has to obey them some p plus, and using those constants we get the that's all we do. Once you get those constants, after those constants it becomes quite easy, because oh my gosh, you get those constants, and what we do next basically once you get to the constant, now you're going to do level matching. So in the here the mass is simply p square, minus p square, so it's something like 2p plus p minus and minus of pi. Yeah, I remember this one because if I'm correct. Yep, this one I remember. Is this the correct one? Gosh, I'm making some mistake. Yeah, it has to be this one. Yeah, but then we are still left with the normal ordering of problem. Yeah, then similarly goes for the sets of operator. This one are for right moving, these one are for left moving. Now, what is special about these things are what is the special thing about Lightcone gauges? Yeah, the special thing about Lightcone gauge. No, that's all. Yeah, there is this. Yeah, Lightcone gauge. What it does is that these are the only oscillators which are independent. But if you give these, if you are given these oscillators, if you are giving these operators, and you have the whole system done. So you got rid of the cage. So because these are d minus 2 operators, and there's 2 because one is left moving and another one is right moving, so you get total number of operators this, and these are called transverse operators. Mode, you can call transverse mode as well, and they call it transverse mode, but yeah, that's all. But when you are writing it an operator and you get rid of it, the normal ordering problem, which is done using zeta regularization, you get it in form of, and they use this notation. Yeah, I don't remember it, but this one is, I'm pretty sure, because this, for an negative n it becomes creation operator, and for positive n it becomes annihilation operators. Minus, damn, I forgot this one as well. D minus 2 by 24, I guess. Yep, that's how you get D26, if I'm not mistaken. Yep, that's all. If you use the left moving modes, you get an this is what you get. Now you fix D. I will just give the argument he gives. You use alpha as a creation operators, and yeah, since we are doing with quantum canonical quantization, you have to give the operators. So alpha are the usual creation and annihilation operators, and we have one operator for x plus and p minus, which is given minus I and xi pi, which is not xipi, it's xipj, which is given by I delta ij. So basically, I will give the argument that you operate, you take the ground state. Ground state is a vacuum, and what is special about this is n will be 0 for this case, so our m square is of form minus 4 by alpha dash d minus 24 4. And then he is not able to get the dimension, the value of d by vacuum state. He gets it by using first one particle state. Now for this case, since we are getting mass as negative, although d can't be negative, that's the dimension of target space. He talks about tachyons, and tachyons lead to unstable maxima of the tachyon fields, potential of tachyon fields, and there's this problem which is there, and we can get rid of it using superstrings where we add fermions on the world shed. Yeah, that's all. After that, I don't think using one particle state he was able to get d equal to 26, because the idea runs as follows. For n will be 1 for d equal for one particle. I will do it tomorrow, and m has to be 0, such that we get a Lorentz invariant field, Lorentz invariant theory. So for that, it becomes you solve this equation, you get d equal to 26. And there's still a problem, we don't know a. I will go and get it tomorrow. Did I mention a? No, it's not mentioned. It gets yeah, that's all I remember. But if I take massive particles, basically state with more than one particle, then we see that once we have fixed all these things, the d has to be 26. We don't find any problem. That's all there. Yeah, that's all I remember.